So we have covered several Noether's theorem, Lagrange equation, equations of motion, and just a few problems here and there. So let's do some more problems. Let's find some applications for all of the stuff that we have done so far. So here's a problem, and it's a bead on a rotating hoop. So actually I got this problem in one of my exams in mechanics, gather mechanics. So it's a painful one to remember. And I'll let you know why in a little bit. So we talked a little bit about something like this. Let's say that I had X, Y, and Z here. So you know X, Y, Z. And then I would have a rotating hoop. It's supposed to be a hoop, so it's an oval. All right, so that doesn't work. All right, so imagine that this is a hoop. It's supposed to go back on itself, right? Perfect hoop. And then there's a bead somewhere here. So that bead is there. This hoop starts rotating. What's going to happen to the bead? Does it stay on the bottom? Does it go up? What do you guys think?
What is a bead?
A bead is just like a little thing that can glide on the hoop. Like imagine a little piece of rock with a hole and then the wire of the hoop is passing through it. So what's going to happen to the little bead? So here's the bead again. Is rotating, let's say, in this direction. Then the bead should start going up to here. Does that make sense? In a hoop, it's going faster and faster and faster. It starts going like this. You could also grab the bead and move it up and down. Okay? So now let's define things. Maybe it's easier to draw here. Here's the hoop. Here's the bead. This is the axis of symmetry. And then here's the center. And I can go from here to here, define it. First, the radius of the hoop is 8. And then we also have that there's an angle that this makes right here. Let's call this angle psi. This thing is rotating around the z-axis, so it has an omega rotation speed, right? And then as it rotates, so let's say that this is the x and y. When it's rotating, if it was on the x, so this is the z plane, x plane, cx plane right here. If the hoop was planar in the cx plane, then the angle that it's making is 0. But then if not, it has an angle right here. And let me call that angle phi. Does that make sense? So if it was xc plane, exactly that's 0, but it's rotating like this. So that angle that it's doing of the hoop, that's your phi. Okay, questions? We're good? All right, so those are the definitions. Now, what we have is a system with a holonomic constraint this holonomic constraint is going to be time dependent. The constraint is that the bead is attached to the hoop, so it has to follow the hoop. There's no way for the bead to move without the hoop. Then it's rotating with the frequency omega. It has a mass m. Hoop rotates at omega.
So the bead is tied to the hoop.
Mm-hmm. It cannot move outside of the hoop.
I mean, let's say we have a hoop and at the end of the rope we have this tie, and then we are just rotating it, and it's making us circular.
Right. So the hoop is just somewhere, and then you're rotating it like this. Yeah.
Exactly. Okay.
Yeah.
That makes sense.
Mm-hmm. It moves without friction, and what we want to do is determine the motion of the bead. So how many degrees of freedom do we have? We have this degree of freedom, right? For the bead. The bead can move around the hoop. So that's your degree of freedom for the bead. And it's just the angle that it makes with the vertical, right? So here's the vertical, and that's the angle that it's making. So we can tell where it is. And if we go to Cartesian coordinates, so we can write in Cartesian coordinates, the position is going to be x is equal to a sine of the angle that is making times the cosine times omega times t. So that's the position in the x-axis. So if omega is 0, right? And you would just say what is the position is related to this a sine. But omega can be non-zero, and then it's rotating around, and that's how it's changing its position with that frequency of rotation. The y one is almost exactly the same, the y position, and it's also an a. But then this one becomes sine omega t. Yeah, yeah. And then the position C is given by A minus A cosine of the angle psi. So we know that our degree of freedom is this psi. So now what do we have to do? We have to write the Lagrangian in terms of the generalized coordinate that is psi, not x, y, and z. So we know what the Lagrangian is in Cartesian coordinates, right? So t is equal to 1/2 m dot squared plus y dot squared plus c dot squared, right? Mm-hmm. Oh, okay. So let's say, what is your position when the angle is 0?
Equals 5.
0, right?
Yeah.
But then if I put 0, and then cosine of 0 is 1, so I will have a minus a. And then if the angle is 180, then I have the thing is up here. So that's just because when the angle is 0, it has to be 0. When the angle is 180, it has to be a 2a. Right? So that will give you the 2a's. A minus -1 times A.
Yeah.
So we have that kinetic energy. And then if we substitute in, so you have to grab and take time derivatives of this guy, right? Dx, y, and c to get those x dot portions, but you can do that. It's just a little bit of taking derivatives. And what we get is 1/2 ma squared. And then the angles, this one squared plus omega squared sine squared the angle. So one in Cartesian coordinates, the other one in the coordinates that we care about, which is the only degree of freedom that we have. Questions? We're good? All right. So then we also have the potential energy, and my potential energy, well, that one was really simple, right? Because it's just this guy. But then now I have to write it. And I'm going to ignore an overall constant here. I mean, it's potential, right? So if you add a constant, remove a constant, it's the same. And you can do that. And once you do that, you just get negative mga cosine c psi. So this guy, I don't care about, right? It's just a constant to my a constant that gets added to this potential. So I don't care about it. All right, so now here's where this gets interesting. We look at it, we take find the Lagrangian, we take this one and subtract this one, right? And if we look at it, our Lagrangian is actually gonna be really nice. And I could even separate it into something like this, ma squared times 1/2 psi dot square, and then minus an effective potential. Here, I just lumped everything else that is related to psi, not to psi dot, into the effective potential, where I have that the effective potential is given by 1/ma squared. And then here I have negative mga cosine psi minus 1/2 ma squared omega square sine square psi. So I have a kinetic term and a potential term. Everything that got lumped here is because it's only the size, not the size out. All right. Questions? No, we're good? All right. So at this point, I can derive the equation of motion. And actually, the equation of motion is kind of complicated, but if I want to write the equation of motion, where's my pointer? Okay. I can write it down because it's going to be this is equal psi double dot is equal to just the derivative of the effective potential with respect to psi. Okay, any questions? So that's what your problem could be asking you to do, right? So once you solve all this, you get this nasty equation, but you can derive it. It's not too bad. Now you have the equations of motion. And the next thing that could be asked is, what are the stationary solutions for this system? Okay. So this is what I got asked in was one of 3 problems on my mechanics exam. What are the stationary solutions? So the first one was derived that it doesn't take too long to figure out what are the stationary solutions, because those would happen when this guy is equal to 0 and this guy is equal to 0. So what we're solving for is basically, when is this one the effective with respect to psi equals to 0. So we can go back at it. This is the effective potential. You just have to solve for when it's 0. You do the math and you can solve it, right? Well, let me sketch. Let me give you when that happens. So remember, this is the equation we're looking at. We want to make this equation go to 0. So I have this one is equal to this one will give me the 0. And it's basically G sine of psi is equal to A omega squared sine psi cosine psi. So what that means is I could take, this is being shared, I believe. So let's talk about 3 different cases now. The first one would be when the omega is equal to 0. What is omega equal to 0 gonna do? Well, in that case, we would have that this is the effective potential. And then this is a straight line. I drew a straight line right here. I don't know why it comes all crooked on the screen. So this is psi.
I have a question.
Yeah.
How can we have omega equal to 0? That means the whole set of like problems.
Yeah, so you have the hoop and it's not gonna be rotating yet.
Yeah.
Yeah, you just leave it without rotating. So if you have a hoop without rotating, right? You look at this equation. So x is always going to be just this part. Y, because it's on this plane, is going to be 0 all the time. And then c is just going to be whatever height it is.
Oh.
Okay? So yeah, you can have that omega is equal to 0. All right, so let's say psi can go from omega from 0 to pi. And if we look at omega is 0, let me use this color for this. For the potential, the effective potential, we're gonna see that it should go something like this to this. So this is omega is equal to 0, and it has this shape. What are the what can happen here? What happens at psi is equal to 0? What's happening at psi is equal to 0? Is that a minimum point or not? So look, if I put it here, what happens to it?
Negative potential, so it feels worse. But falling back down.
So yeah, all right, I put it here. What happens to it?
Again, feel force turns.
And then it stops here, right? So this is a stationary point. Okay, what happens if I put it on the side? Yeah, it's unstable, but it's stationary too, right? So this point is stable, is stationary but unstable. It's stationary but stable. So let me grab your pencil, right? If I put it like this, and I'm careful, what's gonna happen to it? It can stay balanced on the leaf, right?
Yeah.
So that's unstable, but it can stay there. So that's what happens here. So this is stationary but unstable, stationary and stable. Does that make sense? Yeah. All right, so this is stable. This is unstable, but can also stay there. All right, so what happens if we increase omega now, and we start getting omega to get higher and higher and higher? Yeah,
How would you classify pi with two? Pi is equal to pi with two.
so this is my pi over 2.
Yeah, so since that's like in between stable and unstable, is there
Yeah,
anything
if you
special
put it
about
on pi over 2, not really. At this point, it's just gonna go down all the time. Right, so this is pi over 2 right here. You put it there, and it just goes down.
it? Or, well,
Is omega 0? No. All right, so what happens if, well, actually it can never go up because on its own, right? Because the
Yeah.
potential is against it. All right, so now what happens if we increase our omega? So omega is not going to be 0. It's higher than 0. But I'm actually going to put a limit on this. Omega squared is going to be smaller than G over A. And here's again the potential. And then G over A is just constants that you see there, right? So if we have that, now let me get another color for the pointer. This is the line for that. So here it passed exactly through pi over 2. In this other case, if we did that, it's gonna be 0. Oh my gosh. Microsoft, you suck. And then it's gonna pass through here. And then it's gonna rise harder than before and reach this point too. So now, if this is rotating below this speed, angular speed, we see that the 0 got shifted, pi over 2 is now here. So that means that it's gonna be easier for it to fall down here than when it's rotating. Okay? And it just got shifted like that. And then the reason, the final thing that I want to show you with this one, let me do it in orange. If we have that omega squared is bigger than G over A, we're gonna get that this actually becomes a loop around here. And then it does this, just like before. So for the green one, this is stable, this is unstable. For the orange one, this one's unstable. How about this one? There's a minimum right here, right? Is this stable? And how about this one? That one becomes unstable. So this one is stable, unstable, equilibrium, stable equilibrium, unstable equilibrium. That's for the rotating bead. And I messed up that one on my exam. I thought that this was stable. So yeah, that's why I'm always going to remember that this is unstable when the speed is higher than that. All right, so this analysis here is very sketchy in that I just did the sketches, right? That's not a plot. A plot would be that you actually plot the thing and it looks like the equations that you're using, which I could do in Mathematica, and it would probably take less time than drawing this using Microsoft PowerPoint. So at the bottom of the hoop is stable only up to a certain speed. Once you get past a threshold, then the stability comes here. And you'll see that because if you were trying to do that, you'll see that the beat starts and it's going to stay stable there. Any questions about this problem? No? All right, so now let's do the double pendulum. No, I'm just kidding. We'll go back to the double pendulum because it's really complicated, but let me set up this other problem. The double pendulum is very complicated because he can give you chaos. So I guess you could say it's complicated or it's really interesting. I don't know. And it's two-dimensional because there are 2 degrees of freedom. So at this point, let me talk about an spherical pendulum. Our pendulums have been allowed to move in just 1 dimension. But now what if we have a spherical pendulum, which is basically allowed to rotate in 3 dimensions? So this is complicated to draw. Let me go back to the board. All right. So what I'm thinking about is the following. We're going to have a sphere. There's your sphere. There's going to be an axis passing through its center. And then if we look at it from the center to here, there's our mass. And here where our mass is, there's actually a plane inside of that sphere, right? So there's an axis right here, and there's an angle theta between this, whatever length it is, and the mass attached to it, to the center of the sphere. And then the other thing that I have here is that for this axis, this, so here's the plane, right? Right here. So this is where the axis and the plane coincide. And then if I look at this guy, there's a projection that goes in this direction into the plane. And that one has an angle right here. And for that, I'm going to use the phi as my angle. So is that angle clear what it is? It's like the projection on the plane of this one. So for instance, if the mass is right here on the sphere, this phi is 0. If it's over here, this phi is 90 degrees and so forth. Does that make sense? XY plane is this one right here. Yes, no? All right, good. So let's go back to the spherical pendulum. It has 2 degrees of freedom. We have the theta and we have the phi. So 2 degrees of freedom. Theta and phi. Theta can go from 0 to pi. In our units. And phi can go from 0 to 2 pi. So just like a spherical coordinates, right? So if we want to write the Cartesian coordinates, this is going to be x is equal to the length of the pendulum, cosine phi cosine theta, y is the length of the pendulum, sine phi cosine theta, and then c, I'm going to choose negative here, L cos theta. So if we write the Lagrangian, we're going to have the usual one, right? 1/2 m. And then here I would have the x dot squared, y dot squared, c dot squared, minus mgc. Or if I write it in the coordinates for my degrees of freedom, for my generalized coordinates, I get 1/2 m L squared theta dot squared plus phi dot squared sine squared theta plus mgl cosine theta. All right, so things to notice here. Is phi located in the Lagrangian? No, right? So then we call that one, we call that an ignorable quantity. So the first thing to notice, phi is ignorable. And from Noether's theorem, we have that there's a quantity, I'm going to call it J, that if I take the Lagrangian and differentiate it with respect to phi dot, I'm going to get ml squared phi dot sine squared theta. And this is always a constant. So this is from Noether's theorem, right? That we know that there's a symmetry here and that there's a constant, a conserved quantity. So that J is related to the angular momentum. Salini, what is the angular momentum that we're talking about here? Do you know?
Yeah, the momentum of the spherical, the ball revolving around the z-axis.
Yeah. So that's because of this angle, right?
Yeah.
So that's why it's not L, but it's J. All right. So this is the J angular momentum, the angular momentum in the phi direction. And then we can do Lagrange equation with this Hamiltonian. I'm going to do that in the next class and then use this thing that we just came out that is a constant, the angular momentum, and look at our equation of motion. Looks complicated. Now we insert our angular momentum, conserved quantity, and it gets easier to interpret. Okay, so that's all the time I have for today. Yeah.
X should be L cosine by sine theta.
Oh yeah, you're right. Sorry. Sine theta. Thank you. You're right. Because yeah, the sine theta up here, sine theta up here, and then cosine theta with the C. Awesome. All right, so remember, homework is due Wednesday morning. Hopefully that doesn't change your plans too much for Labor Day weekend. Okay. Thank you, everybody.